record. So now we're officially recording. Good evening. And again, if you have any questions, any other questions in the homework, feel free to ask me by email, or we can also set some Zoom meetings for your group or individually. So not a problem at all. Let's get started here. So for this class, we're going to be using two data sets. We're going to be using the sales DTA after and first cost rate DTA. So if you want to follow along, just please upload them into your box folder. And today we're going to be talking about regression analysis. So a refresher for those of you that did take econometrics. For the ones that did not, this can be a little bit more challenging, so please don't forget to, review the material in the book and also ask questions, but hopefully we'll be able to clarify lots of concepts tonight. So this material is in chapters 5 and 6 from your book, and we may also get started on 7. Let's see how it goes. I don't want to rush things. I prefer that you guys stop me whenever you have a question, and then we can move along. So last class, we're talking about what are the basic conditions for us to be able to generalize regression, to be able to estimate this regression line when we have more than one treatment or multi-level treatments. So in the real world, we know that we just don't have these on and off variables such as advertising in the example before, but we can have different levels of advertising, different levels of prices, and then we ask the question of, what are the general conditions that this regression line should meet in order for me to be able to estimate my betas, right? So we talked about the moment conditions. So basically we are going to require two things. We're going to try to come up with estimates in such a way that our predictions are going to be well balanced, in the sense that there's going to be errors that we're going to be making, residuals, positives and negatives, and we want those to balance out. So this is what we mean by the first moment condition. We want the mean of our residuals to be equal to 0. On average, we're not going to be making systematic mistakes. And the second one is that the mistakes we make, the mistakes that we do make, they should not be correlated with the treatment, right? There's not a tendency to always undershoot for certain levels of my prices and to always overshoot for other levels of prices in a sense. So we don't want any strong relationship between my mistakes and my independent variables. So if I show those two lines to you, which line would you prefer based on these two sample moment conditions? Which line is better in this case, line A or line B?
Line B.
That's exactly right. Why is that the case? So looking at this example, you guys got it. Many of you answered letter B, line B, and we can see that line A systematically underestimates the data, as opposed to letter B, line B, in which the mistakes are more well balanced, right? So line B satisfies better the first moment condition. Let's see the second example. Let's go one step ahead and let's now compare these two lines once again. Line A in red, line B in blue, which one is better? So we have a couple answers here. Most of you guys still choosing line B. And line B is actually the more appropriate line in that case. Well, both of them, line A and line B, they are actually well balanced in terms of the first condition. So we don't have these, on average, they tend to balance the data well. But the problem with line A is that line A exaggerates the slope in the sense that if you think about your price levels, for low levels of prices, we see that line A always overshoot. And for high levels of prices, we see that line A undershoots. Line B doesn't have so much that tendency. So therefore, when we think about a change, the effect of a change in price on my profits, Well, if I go with line A, this effect is going to then be more exaggerated than what it should be. So here, when we think about the sample moment conditions, well, we want to break down this dependency of X, in our case, price, and those residuals. And line B does that a better job in that sense. So we also want to go with line B in that sense. So line B is the answer for both examples here. Well, it turns out that those sample moment conditions, they can be a little bit cumbersome if you think about, many variables. That's what we want to do. When you guys are doing your job as analysts, you're going to have many determinants of the outcome that you would like to analyze. So we need some practical method in order to attack this situation. And it turns out that there is a mathematical equivalence between the moment conditions and the OLS, the ordinary least squares method that you guys, many of you may have heard before. So the OLS method, what this method, this minimization is going to try to do, again, we're optimizing here, we're trying to find parameters that are going to fit the data the best. So what this method is doing is calculating the residuals, which is the difference between what I observe and what I predict. Then I take those residuals, this is in parentheses here, this is just my residual. I square each one of them, and then I make the sum of these squares as minimal as possible. So the computer behind the scenes is going to be calculating those betas, looking and checking every time to see if the residual sum of squares, what is the residual sum of squares? The amount that my regression have missed, was not able to explain, my mistakes. I want that to be as minimum as possible. And that's essentially the idea behind the OLS. And that's what Stata is going to be calculating for you. So let's just hop onto Stata and just remind ourselves about this method and see how can we estimate this regression. This is something that we're going to be doing in our homeworks from now on. So if you can just load data set cust rate, let's go ahead and estimate this equation together. This is a multiple regression model. So what is the syntax? You can type regress or reg, and then you can just go ahead in this panel to your right and double click on the variables. The order is going to matter. You want your Y variable first. So I want to see here the influence of income, age, education, and marital status on how customers rate my product. That's the example that we're looking at. So my outcome variable is cust rate, and then I have all these independent variables. Those variables that come after here, they are the X variables. The first variable is always the Y variable, the variable that I'm trying to predict. I'm trying to predict customer rating based on observing a certain income, the customer's age, the customer's education level, or whether or not the customer is married. If you press enter, what do we get? We get our regression output. So this is, you can also do this in Excel, but this is a very important output that we get because we have everything that we need here. And we're going to be talking about some of the things in this output, but I want you to first focus on the first column. So here we have our baseline, so that's the constant term, and then we have our beta hats for each one of the variables in our model. So this model is saying that, customer rating and income, age, education, they are positively related. Marital status, so if the person is married, then we see a negative relationship, and we also see a baseline beta over here. That's your beta 0. The minus 4.73 is your beta 0. So immediately you have those beta hats. So behind the scenes, after doing all this minimization, we come up with our estimates. Those are here in front of us, right? So how can we interpret? If I asked you guys, can you tell me what these coefficients really mean? How do you interpret the coefficient on income, age, education? So for the ones that have engineering training, this is nothing else than a partial derivative. So the idea here is, what is the associated change in rating once we increase our variable in one unit, holding everything else constant? So basically this model is telling me that, you know, if I increase the customer age in 1 extra year, I'm gonna see an increase in customer rating of 0.25. That's what the coefficient in age is telling us. Holding income, education, marital status constant. It is very important that you mention holding everything else constant, because this assumption is very important. Once we're including all these variables there, we're saying among people with the same education, with the same marital status, with the same income, if I increase age in 1 extra year, the change that I'm about to see in customer rating of my product is an extra 0.25. So it is very important that we know how to interpret what the output is giving us. What about the variable merit, right? So merit is a little bit different, because merit is not a continuous variable. It doesn't take on many, many values as opposed to income, age, and education. Those are all measured in dollars, in years, but merit is just a yes or no, 0, 1 binary dummy variable. So the interpretation of merit here would be, relatively to single people, married people discount the rate in 0.26. So we have a negative effect if the customer is married, a tendency to evaluate the product downward. Baseline minus 4.73 doesn't make any sense. Sometimes that is going to be the case in many of the regressions that we run. Sometimes beta 0 has a meaning to it. In that case, it doesn't make sense to think about a customer with a rating of minus 4, right? So here, what is the interpretation of your constant term? The constant term is the baseline rating that you get when all the other variables are set to 0. So if you set income to 0, age to 0, again, this doesn't make a lot of sense, education to 0, and married to 0, which will be single, then customer rate is going to be minus 4.73. And I have written all these interpretations here for you. Very careful with the language. You say beta 1 is the associated change, not the causal effect. For you to be able to claim that income or age or education status is causing something, well, we're going to see in this class that there's a whole range of assumptions that we need to assume. For now, what we can say is that we see some associations, we see some correlations. That's what we see between X and Y. That's the best we can do. Okay, so be careful with how you interpret. If you don't write holding everything else constant, you might lose some points, because this is really what allows us to be able to reduce selection bias. We're comparing people with the same age, education, and marital status, and we're saying, hey, if you change income in 1 extra unit, this is what you expect to see. So when we are writing holding everything else constant, holding age constant, education, this matters. That's what I'm saying. It's not just a cosmetic thing. It's really allowing us to reduce selection bias, something that we so much talked about last week. Well, when we run a regression, and again, very easy, we just type reg and then the outcome variable and the X variables, we are left with our beta hats. So the first column, it's all your beta hats, your estimated betas, and what they are doing is coming up with estimates for your population parameters. So we like to think that when we're running a regression for correlation, that there is a population out there. Let's imagine this population are all US customers. And if we were to include every one of them and run a regression, we would get beta 0, beta 1, beta k without a hat. Those are the true, real parameters, population parameters. We don't have the population, we just have a sample of that population. So we come up that we hope is random, and then we come up with estimates. Those are the beta hats. So one of the questions that we would like to ask is, are those beta hats that we get when we estimate population parameters using just the sample of customers that we can feasibly have, are they good guesses, right? And the measure of good here in the statistics that we're going to be considering in econometrics is consistency, right? So what consistency is telling us is this is going to be considered a good estimate as long as this parameter that you have estimated, beta hat, converges to the true population parameter as the sample size gets bigger. So that's the idea about consistency. As you increase the sample size, your estimated coefficients are going to be converging to the true betas, the true population betas. So the question that we need to ask is, after running the regression, what do we need in order to guarantee that we have good betas, that we have good beta hats? The only thing that we're going to ask for correlational regression is that we have a random sample. As long as you have a random sample, you're fine. You're going to have consistent estimates. If all you're trying to do is correlational regression. See, I have not said causation regression. For causation, we need something else. But if all you're trying to do is come up with predictions, is to be able to come up with predictive, passive prediction, all you need is random sampling, okay? Well, besides being good guesses, we also would hope to do hypothesis tests. We would like to, be able to conduct tests of all sorts and build hypotheses and build confidence intervals. That's something that you're doing in homework too. So what do we need to be able to know the distribution of our betas, right? How do we do hypothesis tests after we have run a regression? Well, we want to invoke again the central limit theorem. So we're going to require random sample, we're going to require large sample. How large? Well, now we're making predictions that involves many variables. So we're going to require a good rule of thumb here is going to be 30 observations per parameter that you are estimating. So if you have 3 variables in your model, let's say income, age, and education, then you need 120 observations. So you need an extra set of 30, because remember that we're also estimating the constant term. We're also estimating the beta 0 term. So we're going to be needing here for 3 variables. So if k is equal to 3, we're going to be needing 120 observations. So we need random, we need large, and we're going to add another assumption that we called homoscedasticity. Homo means same, and scedasticity meaning variation. We're going to ask that the variance of our error, of our residual, is constant. This assumption is not necessary for consistency, but this assumption just facilitates the calculation of that distribution. So it's more of a convenient assumption to have. You would also be able to perform hypothesis tests without homoscedasticity, but we add this assumption to facilitate the calculation of the standard errors. Okay, so if that's not true, it just means that your standard errors are going to be more complicated. Once these assumptions are satisfied, then you can proceed normally with the same idea from last week. You can compute your t-stat, and your t-stat is also going to be given to you in your regression output, and go ahead and do all hypothesis tests that you want. So here, if you want to test a hypothesis that your coefficient is different from 0, you're going to set the null hypothesis with the equality. Again, if we reject the null, that means that our coefficient is going to be statistically different from 0. That means that we have significant effect. So let's see where we can find all this information in the output that I just gave to you. So going back to the regression here, let me just show this one more time. This information is going to be in the third column. So here on the third column, you're going to have the calculation of your t-stats. They are ready for you, and all that does is to divide. They test the hypothesis that each of the parameters is different from 0. So here, you can do this manually, but 5.33 is beta hat divided by the standard error. You don't need to divide by the square root of n anymore. This is just built in there for you. So you take this number, beta hat, you divide by the standard error, which already is divided by the square root of n. You don't need to worry about that. And you immediately is going to have your t-stat, which is also displayed in front of you. You can do this manually. You can use the output in front of you. And here we can see that our t-stat is large. 5.33 is greater than 1.96. So, and it's even greater than 2.58. So we can reject at 99% confidence level. We can, so income is significant, age is significant because it's greater than 1.96. Education, not significant in that case, and marital status here, not significant. Okay, so that's how you would quickly look at the output and immediately see which variables are statistically different from 0. In this model, once again, income, age, they all pass the test, but the other variables are not significant. They are not statistically different from 0. Okay, so they are not helping me. There's not a significant correlation between education and how the customer is rating my product. This is important, right? I want to see which variables matter most in my product rating. And I see here in this model that income stands out. It has the highest T stat from them all. The fourth column, again, is going to give you the p-values. So again, a very easy way for you to conclude. You can look at the t-values, or you can look at the p-values and see if they are less than 5%, if you want to be 95% confident. So again, we have a very low p-value, the lowest the better. The first one, highly significant. Second one, 1.3% significant. All the other three have p-values that are higher than 5%, so I'm going to fail to reject the null hypothesis. I cannot say that they are statistically different from 0. Okay, they're actually not, I'm going to be failing to reject. I can also build confidence intervals just the way we know. We have the standard errors, we have the sample means, which are here the beta hats. So you can calculate confidence intervals for each one of your betas, and that's the last two columns. So I see here that 0 is not in here for the first estimate. I don't see 0 in there, so that's good news. That means that income, once again, is statistically significant. So all those columns that comes with your regression output, they contain great information that quickly allow you to just run your eyes and check which variables are more important in explaining your outcome and the level of significance. Let's say, hey, Juliana, I don't want 90%, 95%. Stata is giving me the 95% confidence interval. What if I want the 90%? You're going to type a comma, and you're going to write level, and then you specify whichever level you want. Let's say you want to be 90% confident. There we go. Stata will compute the same calculation, but now with a 90% confidence interval for you. So very convenient whenever you want Stata to introduce options for you. We do usually that with the use of a comma after the command. So following the comma, usually those are the options available for you. Please feel free to interrupt me at any point. So again, those hypothesis tests, you're going to proceed normally. You're going to use the same critical values as before, 1.65, 1.96, 2.58. And again, you can look at confidence intervals, you can look at your p-values, you can look at your t-stats. given that the sample is large enough, the t distribution approximates the normal distribution, so you're fine just using those critical values. You don't have to worry about going to Stata and computing the specific t critical value. You can just approximate those with the normal 1.65, 1.96, 2.58. So those numbers are really worth remembering. Usually a good rule of thumb is 2, right? So some people cannot remember 1.96, so they say, okay, if it's bigger than 2, I'm going to say it's significant. So something like that. So just to be easy for you to remember. So here, just saying what we have just gone through. Another way you can do tests in Stata is using the test command. So if you want to test whether income is really equal to 50,000, you can type test, name of the variable, equal, the double equal sign. Remember that the double equal sign is the logical operator for equality. And then the variable that you want to, the amount that you want to test, the constant that you want to test for. So let's say you want to test if income is equal to 50,000, then K is going to be 50,000. You can do that normally. You're going to get a p-value. The p-value is always going to help you conclude about the test. You want your p-values. If you want to reject at 95, you want your p-value less than 5%. If you want to be at 99, you want a p-value less than 1%. If you want to be more stringent. Which one, Seth? Which example? Sure. We can go in here and just type test. Sure. Test. So Seth is asking me to demonstrate the command. So test, then name of the variable, let's say income, equal, I want to test if that income is equal to 50,000. There we go. So I'm going to get a p-value here of 0. So that means I can, since my p-value is less than 5%, you don't have to worry about the f-value. The f-value is just the square of your t-stat. But for you to quickly conclude, you can just look at the p-value and see the p-value. The p-value is 0. 0 is less than 5%. So I'm going to reject the null hypothesis that income is equal to 50,000. Okay? So again, another way of performing the test. But you can test all sorts of hypotheses, but just by knowing the standard errors, right? So in your homework, you can use beta hats minus the null value, divide that by the standard errors, and there you go. Your t-stat is going to be there for you. If that thing is greater than 1.96, go ahead and reject. And I think that's going to help you a lot in homework. Okay? Perfect, Seth. So moving along. Yes.
This is Manish. I have a question. So if the p-value or the t-stat, because they remain constant regardless of the confidence interval, is a certain value, and if we change the confidence level, the confidence interval would change, right? Is there a situation where t-stat would be, for example, say greater than 1.96 or say 2.58, which is 99%, and that's true for, and t-stat obviously won't change with the confidence interval change, but the confidence interval now includes 0. Is there a situation that we can encounter like that?
Possible. You gotta come up, because then your t-stat is also gonna be rejected at that other level that you're mentioning. So all the conclusions need to align. There's no way we can have a discrepancy between the 3 measures. They all have to come up with the same conclusion. Okay, in a confidence interval, you're gonna multiply the standard error times the critical values, right? And then come up with that range. But they need to attain the same conclusion.
Okay, appreciate it.
Okay? So again, another way for you to check, to be vigilant of that, to be aware of that. Perfect. You guys are all on top of the material. Wonderful. Okay, we have estimated a regression that's nice and easy. I think it's sweet in Stata. Nothing to worry about. What can we do with that? What can we do with that is going to depend on our assumptions. So far, we only asked that we have a random sample. And we also added homoscedasticity for cosmetic reasons to help us calculate standard errors. once we run a regression, 100% of the time that regression is going to be useful for passive prediction, right? What is passive prediction? Well, there's a bunch of axes out there, and we see a relationship of those axes and our outcome variable, and we're saying they are moving together and they have a certain behavior. We're going to use that behavior to try to make predictions. This is entirely different than saying there is this variable that is causing customer rating. This is entirely different. In a correlational regression that is useful for passive prediction, we're saying we're only observing those patterns, those correlations, and we're using those correlations to make predictions. We're not claiming those axes are causing Y. This is causality, something that we're going to be talking about a lot as well. So once we run this correlational regression, we're going to use that regression to make a prediction. We're going to say, for instance, if I have that profile, if I have a customer who looks like that, has a certain income, age, level of education, that customer is married, what do I predict that the customer rating of my product is going to be, right? How do we do that prediction? And again, this is a question in your homework. What you're going to be doing then is use your model and then substitute for the values. Using your beta hats, you're going to substitute for the values of that particular customer. So don't forget to add your beta 0 here. Some people will forget to do that. Don't do that. I don't want to deduct any points. And then you have your beta 0, beta 1 times income level, beta 2 times age, beta 3 times level of education. Then you know that the person is married, so you load that dummy up, and you know that this customer is going to have a rating of 77% of your product. So let me go ahead to the chat. Let me visit the chat here because it seems that we have a question. What if we have p-values that are very right there at the border? This is a situation where, you know, maybe you want to restrict your level of confidence and say, okay, this is just borderline. We mentioned that. So in a statistic, there's no hard rules. But if you are right in there, hard to say, right? It's very, very hard to claim that the variable is statistically significant. So you want to comment on that. So that barely passes the test, right? The highest, the better. The higher the t-stat, the better. So it's usually also a matter of magnitude. You really want your t-stats to be high as possible. If it's right in there, you also want to make a comment about that. So once you run, yes?
No, sorry, this is Manish again. I have another question about that model that you're talking about. What if a value is insignificant? Do we deduct that from our model, or do we keep that beta value into our model even though it is insignificant?
Yeah, the problem is that if the variable is insignificant, that variable is 0. That parameter that is a positive 0.25 here, let's say for age, for instance, right? That 0.25 is statistically 0. That's a good question. You want to add that, but you want to comment on the fact that this variable is not significant, right?
So in a situation like that, for example, that variable has a very high value or a very low value and can have a significant dent on, not significant, has a big dent on our final, say for example, customer rate, Y variable.
True.
But in reality, it is actually 0.
It's actually
because it's insignificant. Should we not take it out of the model then?
That's a very good question, Manish. It's a very good question because, you know, even though theoretically people would write that variable in there, that variable is statistically 0, right? It's statistically not different from 0. There's no effect. Actually, that variable doesn't help explain so much. I will confirm that with you. But for right now, leave that variable there because there are other reasons where there are other reasons that we're going to talk about that we want to leave that variable. Let me see. I will go back to that question. Some people write that variable, some people don't. Let me think about that.
Okay, thank you.
Is it typical that that variable would have a large impact if it is showing to not be statistically significant? Because if you look at the way the equation would break out, it would be the majority of your values can be determined by that first beta, and the second two, showing, or the last one,
True.
the last two, sorry, showing to be not statistically significant are only going to move you around by like a total of 3.
Yes, that's right. The magnitude is really low here compared to the first one, right? 150,000. I understand your point. So I will not give you my last word on that, and I agree with all your visions, the one claiming that we should and the one that says we should not. Let me think again about that, and I'll get back to you. I'll send you an email about that question, that specific question. Sounds good. There's also a question here that is asking me, how do I find the minus 2.6068? So this is actually the beta hat from the merit variable. The merit variable, remember, is this dummy variable that is equal to 1 if the person is married. Here we have a customer that is married, okay? So we actually have that dummy loading up in the model, so we need to include that estimate. If we had a single person, if our customer was single, then we wouldn't have the 0.26. And again, we are with a case here that we're including all of them despite significance, okay? And I'll give you my last word on that tonight or tomorrow as early as possible, okay? Let me think about that once again. So moving forward, how do we also compute those predictions with Stata? There is the predict command that you can use that is going to calculate your predicted values. I think we have done this command before. So if you type predict and then let's say you write customer rating fitted with the option XB, this is going to compute the predicted values for you. So let me demonstrate that using Stata. So let's go ahead here. Let's jump on Stata once again. Let's go ahead and go to the model that we have just estimated. So let me run the regression again. The reason why I'm going to run the regression again is that the command predict is going to refer to the last regression that you ran. So here I'm going to type my regression, and now I'm going to compute the predicted values. So I'm going to write predict. I'm going to choose a name, let's say cust rate fit. I always like to write fit or adjusted or anything like that. Remember that this is the Y hat and then option XB. And this is going to immediately create a new column here with the fitted values. Right? So those are the Y hats for each one. So here we have, for instance, a customer that is 27 years old, whose income is $56,402, 40 years old, 18 years of education. The customer is not married. What do my model predict is going to be the customer rating? 34%. Okay. Now, can I compute the residuals? Of course I can. You can write predict and then a name of your choice and then the option residuals. If you type all that, again, Stata is going to create another column for you that has how much were the discrepancy between what was observed and your prediction. So let's take a look at the first column. For that particular profile of customer, my model predicts a 34 rating, and actually the rating was 27. So I overestimated. The actual was 27 and my model said was going to be 34. So I overestimated in that case. Again, Stata is going to compute all that for you really easy. So for each one of your customers, you're going to have a predicted value and you're going to have the amount that you were off, right? How much you missed once you estimate this model, probably because there are other things that matter that you have not included, so there's always some residual, there's always some mistake that you're going to be making. We want that mistake to be as low as possible. Okay, so again, you can use the predict command. When we compute these regressions, when we estimate our regressions, remember that all we're doing is establishing correlations, is looking at our variables and see how they're moving together. So a regression is going to be a regression coefficient here. I think an important result for you to remember is that once you estimate a coefficient, those coefficients are going to be proportional, and they're going to have the same sign as measures of correlation. But would be any measure of correlation? Not really. The measures of correlation, they are very much linked to our estimated betas. Those are going to be the partial and semi-partial correlations. So what is the three measures that we can think about when we're thinking of how variables are moving together? I can have a raw measure, let's say the correlation of rating with income, and you can just type that command in Stata, CORR, income and customer rating. If you type that out, you're going to find the correlation. This is the raw measure. But let's say you want to control for a third variable, right? So you want to see how customer rating and how income move together, but unaccounting for movements that are due to a third variable, Z. Let's say you want to see how customer rate and income move together, but isolating the effect of age, right? You don't want age to be driving those movements. So whenever you want to isolate that effect of a third variable, you have your measures of partial and semi-partial correlations. And if that partial or in that case, semi-partial correlation is positive, your beta is going to be positive. So the betas that you estimate, they're going to have the same exact sign, and they're going to be very much proportional to that semi-partial correlation, that correlation that you get once you hold another variable constant, once you control for the influence of a third variable here, let's say age in that case. So what I think so the book talks about these three measures, Manish. Manish is asking me to go over the measures. So the book talks about these three measures of correlation. Why is that the case? Because a regression is a reflection of correlations, right? We're talking about regression for correlational purposes. So which measure of relationship is being captured by my beta hats? The semi-partial correlation. What is the semi-partial correlation? Is the correlation that I get without the influence of another variable. So let's go over the first one. The first one is the very raw one. So you type correlation, let's say rating and income, and you get this correlation. Let's say it's 76%. Okay, so let me just type that into here, 76%. Now, I want to see how customer rate and how income are related, but controlling for age without movements that are due to this third variable. These are going to be called the partial correlation. And you can compute that correlation by eliminating that influence of age. How do you do that? You just compute the correlation between the residuals. So this E variable here is the residual of the first variable, let's say customer rating and age. You regress customer rating on age, run this regression, take the residuals, which is the part of customer rating that was not explained by age. You do the exact same procedure with your other variable, let's say income and age, run the regression, how income is affected by age, compute the residuals, and now you just do the correlation between the two residuals. Those two residuals, they are free from the influence of that variable Z. So you are isolating, you're saying, what is the movement between rating and income that are not due to age moving around, okay? So that idea of isolating the effect of a third variable is essentially what a regression is doing. when you are including your controls there, your age, your income, your marital status, essentially you're saying, what is the correlation that I get between my customer rating and my income, eliminating the influence of all these other variables? That's why you have the holding else constant assumption, right? So now you can really see why do we need to write holding constant, blah, 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 all my controls. Because really what the regression is capturing is movements, but they're not due to these other variables in my model. That's what the regression is capturing. Is this clear? And the book talks about, and the book is going to talk about many, give you examples of that. Perfect. So let's move along. So here I calculated those correlations for you, and if you have questions, you can always reach out. But essentially, that's what you're doing. So you see that raw, they were moving, they were 76% correlated, right? So when customer rate was going up, income was also going up very strongly. But when you remove the influence of age, this correlation immediately falls to 45. So basically, you're trying to eliminate selection bias here by having these controls. That's what the idea is. But the point for you to remember, the really takeaway that I want you to get from these correlation measures, right, is that when you run the regressions and you get your beta hats, they are going to have the same sign that your partial and semi-partial correlations are going to have. Not your raw one, not the raw, but the partial and semi-partial in your betas. If one is positive, the other ones are going to be positive. If your semi-partial correlation is positive or your partial correlation is positive, your beta hat is going to be positive. That's what you need to remember. Okay, so by knowing the correlation, the partial correlation, you can predict if beta is going to be positive or negative. That's the useful thing for you to also remember, right? So you can immediately predict that. Partial is different than semi-partial. If you go back, so Manish is asking how partial is different than semi-partial. So in the partial, you eliminate Z for both of them, X and Y, right? So you run your regressions, you take the residuals, and you correlate those residuals. Both residuals do not have the influence of Z. In the semi-partial one, you're just holding a variable constant for one of them. So you have the whole variable Y in that case, and you have variable X without the effect of age. So in the semi-partial, you still have some influence of age, but in X, you have removed that influence. You can see this from the formula. Here, Y is coming out as whole. We are not correlating residuals with residuals. We're correlating residuals of one regression with the whole variable, okay? And again, there is an exercise that is posted. You can go over these measures, but that's essentially the idea. You can hold, so, yes?
Under what circumstances would we use the semi-partial? I mean, I understand why would we use partial regression or correlation, but why would we do semi-partial and under what circumstances?
Well, when you're running a regression, you are regressing Y on all those variables, right? So you're controlling for all those variables. So you're getting a semi-partial correlation over there. When you're calculating your betas, you're getting that measure because you have customer rating and you are correlating that with variables controlling for Z's in your regression. So you have that measure for you. So again, basically what we have is we're not removing all that influence from Y, right? But we're still having a measure that is better than the raw measure, that is more accounting for a control, that is more conscientious in that sense. So in a regression, you're actually doing that.
Professor, I kind of get what Manish is driving at. Could you give us a specific example of when we would use that?
You are not, I mean, an example would be, let's say you're an analyst, right? So you calculate those semi-partial correlations. So the practicality of that, besides, the theoretical calculations and things like that, is that You know, you don't know the regression. You don't have data, let's say, but you still can compute those measures, partial and semi-partial. What this is going to tell you is that, let's say you find a semi-partial correlation that is positive. Well, then you can tell that your beta hat is also going to be positive. Okay, so that's something you can say. That's not the best. You don't know the magnitude, you don't know the number, but at least you know the direction. That effect is going to be positive. So that's the practicality. I'm not going to be asking you guys to compute correlations and partial correlations and things like that, but it's just for you to remember that in a regression that is meant for correlational purposes, those beta hats, they are directly related to those correlation measures. Okay? So if you know the sign, if you know whether it's going up or down, you can already link that to your beta hats. That's all that is to say. Okay?
Okay, thank you.
Okay, so I mean, it's not worth going through, delving too much in that concept, because really the practicality, you can run, we're going to assume you're going to have an Excel and can run your regression. But just know that these measures that you get, they're not causal. They're just patterns. They're just co-movements. That's all a regression is. So you cannot make too much out of a regression per se, because it's just computing those co-movements. But again, if you're just trying to predict something, it's still useful. It's not the most powerful thing in the world, it's not causality, but it's still useful. So what can you do with those predictions that are passive? Well, you can try to predict strategies, you can try to predict which employees you're going to hire based on certain characteristics, you can try to predict which campaigns are more successful than others. You can use those relationships, those correlations, semi-partial correlations and partial correlations that are reflected in your betas to then make predictions, right? So just as we did before. So you can use the betas that you have and then try to come up with how much you're going to think is going to be the customer rating for your product. That's something you can do 100% of the time. This is entirely different than saying, I have a variable that is causing my outcome, that is driving my outcome. I have a price that is driving my sales. So correlation is different than causation. You probably have heard this many, many times, right? Here in the graph, we're showing, for instance, divorce rate and margarine. Unless margarine has some effect on obesity and obesity is going to drive divorce rate, I don't know. Very hard to claim that those two things are causal, right? Probably there is another variable out there that is driving this relationship. So when we see things moving together, I see GDP going up. My daughter is also growing up, right? So those things are correlated. They're moving together. But it doesn't mean that my daughter is causing GDP to go up, right? So when we want to take the step further and do the more powerful thing, which is causality, then we need more assumptions. Which assumptions do we need then? Which assumptions do we require in order to say that, hey, our beta is causal? And that's the whole purpose of this course, to find situations where we can claim causality. Because if you as an analyst are going to make a recommendation that, this manager got to increase price in that certain way, that prediction better be causal. It's more powerful being causal, right? So in that sense, which assumptions do we need? Well, the first one is and I think this is also a question in your homework. The first one is very cosmetic. It's just saying, okay, if we're estimating a linear regression model, the GDP better be linear, okay? What do we mean by linear? Linearity. We want linear GDP. So this is all this is saying is that we are going to require that our betas are not something that is nonlinear. So essentially, I cannot have, for instance, I cannot have, for instance, the third one, beta square, right? So here, I have the square of my beta. I don't want that situation. My model is not going to be useful in that case. We want our betas to be linear, but we can have non-linear axis. We can have age square, that's fine. What we cannot have is beta square or logarithm of beta. Anything non-linear in our betas is not going to be possible. If you want to go non-linear, you need other non-parametric methods. That course is not going to talk about non-parametric estimation, okay? But if you want to sit in the world of linear regression, that's what most analysts sit on. You want to be making this assumption of linearity in the parameters. And that's not a very hard assumption because it still allowed you to have non-linear relationships between y and x. What we mean by linearity here is linearity in the parameters beta. That's the first one. The second one is the strong one, is the important one, and it's called exogeneity. That assumption is the main central theme in the course. That's one that you really need to understand. So exogeneity is basically telling us that there should be no correlation between the error term and the treatments that we consider in our model. So this assumption here is basically saying there's nothing out there. Let's think about in our model, right? We had customer rating, income, age, education, other things, marital status, and then we have an error term. So exogeneity is going to fall down, is going to break down if we are able to think about something that is sitting in this error term that is correlated with income, for instance, right? But what could be something that is sitting on your error term that is unobservable, that we have not included in our model, that is affecting income? Can you think about something? And also, of course, affects customer rating. What will be that? Again, age we have already included. Marital status we have already included. What could be something that would be lying in this error term? If we can find a variable that is doing that, well, this is going to break down exogeneity. This is going to lead to that big assumption falling down, and this is going to create bias in our estimates. And the whole strategy that we're going to be facing moving forward is going to be essentially coming up with techniques to be able to reduce that mistake, to be able to deal with endogeneity problems. Endogeneity is the biggest enemy that analysts have when they're trying to come up with causal models, right? So all the econometric techniques that we're going to be learning, the more complex one, the more simple ones first, and then the more complex one, they're going to be counting, they're going to be taking care of endogeneity. That one is really, really a problem for us, right? If your assumptions are satisfied, 1 and 2, you have exogeneity, you have linearity, then you have consistency for causal regression, not for correlational regression, but for causal regression. Remember that for correlation, all we want is a random sample. But for causality, we want random, plus we want assumption number 1 and assumption number 2. If we have that, then we say, hey, we have a good guess of the effect of income in customer rating. Clear? Again, we can use those assumptions plus homoscedasticity to build confidence interval, to do hypothesis tests, as long as we have these assumptions satisfied. And again, same assumptions, linearity, random sample, large, exogeneity. We can proceed normally and build confidence intervals and do hypothesis testing and do all those things that we want to do in inferences. Homoscedasticity, again, cosmetic for easiness of calculation of your standard errors. And then once you're able to establish causality, if you're able to say, hey, I have an exogenous model, I have exogeneity holding on, you're able to say, if I change my price by 1 unit, that is going to cause my sales to increase in that many units. And this is in a causal sense. Variable price is actually driving sales. Not because of a correlation that we see out there, but because of a causal relationship. That's where we want to get ourselves into. We want to be able to do active predictions, and active predictions, they depend on causality. They depend on these assumptions that we have listed. So linearity and exogeneity. We need those two, and random. We need those two important, one plus random, to be playing in causality. So I think this is also a question in your homework. Make sure you revisit those assumptions. When is model fit important? I think we don't have much time left. So I'm going to pause here and we'll continue next class and ask if you have any questions. But this is just basically saying that, you know, the R-square is going to be important if you're trying to make passive predictions and not active predictions. We're going to continue from that on next class. Let me just see if you have any questions. Could there be causality without correlation? Yes, Manish. I can send you an example, but you know, you can think about, you can define variables in a certain way. So you can, I think I can write the text model for you. I'm going to think about the text model for you in which you can have causality and those variables not be correlated. You can have causation without correlation. You can have correlation without causation.
Thank you, Professor.
Okay, perfect. Any other questions?
Thanks.
All right. So if you have any questions in your homework, feel free to reach out. Feel free to reach out for any other concerns that you have. And I don't want to rush things, so I will continue from where I stopped. So next class is going to be chapter 7 mainly, and probably we're going to be starting, if we have time, on two-stage least squares, the more advanced techniques. So next class we're going to talk about simple strategies, and then from them on more complex strategies for dealing with endogeneity. That's essentially what I want you guys to keep your eyes on. I hope you have a wonderful night, and unless there is any question, I'm going to leave you with that. Lots to think about, but hopefully some more clarifications. Thank you very much for joining me live. And for the ones that are recording, please reach out for questions. See you guys next week. Bye-bye. Thank you. Thank you so much.